So notes for 3.3 have to do when substances undergo a change in state or a change in phase. So we want to look at how we can calculate this compared to a change in temperature. Now, we are first going to look at the changes in the two and kind of review if energy is being absorbed or released. So on the diagram here, I have my solid, my liquid, and gas. So I've got arrows on here, and you can see that I have arrows pointing upward. So like this one, and this one, all have to do with the arrow over here on the left that is also pointing upward. So in this one, energy is being absorbed. So and we are talking about heat. This is that Q. So if it is being absorbed, these are all endothermic processes. Also, during this, since we're talking about changes in state, there's something happening between the attractions between the particles, and what's happening is particle attractions are weakening. We also know Q, and it can be an upper or lowercase letter, is going to be greater than 0. So it's going to be a positive value. Okay? So if we go over to the diagram and look at this, we can identify if we're going from a solid to a gas, this would be vaporization. If we are going from a solid to a liquid, this would be melting. Sometimes that is also called fusion. And if we are going directly from a solid to a gas, that is called sublimation or subliming. Okay, so all of those are absorbing energy. If I do the reverse, so on the other side, this would be my arrows going this direction, downward. This would be the reverse. Energy is released. And we're still talking about heat energy. This is an exothermic process. And we're talking about it's changing in state, so particle attractions here are strengthening. And the last piece would be that Q here is going to be less than 0. Oh, that's where Q has that negative value. So this would be if we are strengthening the particle attraction. So in other words, if we're going from a gas here to a liquid, this is condensation. If we are going from a liquid to a solid, that would be called freezing. Or it could be called solidification. And if we are going from a gas to a solid, skipping the liquid phase, we call that deposition. Two examples of where this happens. Deposition would be like when your car's parked outside in the winter and you get up in the morning, there's frost on it, right there. It went from the vapor that was in the air to a solid right on the windshield, so that would be that. The other one would be, a good example would be dry ice. Dry ice sublimes. They use it at dances and events, and so they just set it out and it forms like a fog. It's really carbon dioxide going into the air. So those would be our examples of changing in state and what they are called. So we want to talk about the difference between a solid to a liquid and a liquid to a gas. We will never deal with any problems that sublime or go through deposition. So that's going from a solid to a gas or a gas to a solid, skipping that liquid phase. So we are only going to deal with the two that go from solid to liquid and liquid to gas. So what this is termed between a solid and a liquid, we look at this is called the heat of fusion, or sometimes they call it enthalpy. Either term is correct. So the heat of fusion is, it says how hard it is to change the state of a substance between solid and liquid at its melting point. So that's what it is. How hard it is to change a substance from a solid to a liquid at its melting point. Now, to say it more specific, it is the energy required to change the state, and we're saying between a solid to liquid, of 1 gram of a substance at its melting point. So we know, like when we did labs, we could see where the melting point was staying constant. That's where we're having that change in state. So the units for this, so it's how much energy per gram. So it would be joules per gram. Now, sometimes in chemistry, rather than talking about grams, we like to relate it to moles. It could also be a joule per mole, because sometimes we deal with a larger mass and they like to use moles instead. So if we were looking at something that was melting, I want to write the equation for this. So if I had a substance that was melting, and let's say if I had substance A, so it's going to start out as a solid, I'm going to have to add heat to it, and then it would become substance A, that is a liquid. The change in H for this would be a positive value. And the reason why is because I'm adding heat in. If I was doing the reverse of that, if I was freezing something, I would start out with substance A and it is a liquid. I would have to remove heat from it, and then I'd get substance A, now that is a solid. On this one, my change in H, since I'm releasing heat, this would be a negative value. So you have to recognize if you're losing or if you're gaining heat and then assign it appropriately. Now, the difference between a gas and a liquid. Same thing here. This is called the heat of vaporization. Or we call it the enthalpy. And it is usually abbreviated the change in H, and they put a V as a subscript. I think I forgot to tell you up above when we did the enthalpy for the other one, this one would be called the change in H, and it would be a small case, lowercase f for fusion, if we were going from between a solid and a liquid. So there's a different name for them depending on which phase change we're talking about. So this one would also be how hard it is to change the state of a substance between the liquid to the gaseous state, or to the gas state, at its boiling point. So, more specifically, it is the energy required to change the state of 1 gram of substance from a liquid to a gas at its boiling point. Same units for it. It is going to be how many joules per gram, or it would be joules per mole. Now, if we wanted to do this one, so if we change something to a vapor, my equation would be, I would start out as substance A, that is a liquid. I have to add heat to it, and then it would become substance A as a gas. I'm adding heat to it. My change in H for vaporization is going to equal a positive value. If I was doing the reverse, condensing something, I would start out as substance A, that is a gas. I'm going to release heat, and I would get substance A now, that is a liquid. On this one, my change in H, B, heat of vaporization, is going to be a negative value. I need to go back up here on this one. These changes in H's here would have a little F on them to say, yeah, we're talking about heat fusion. Okay, so let's see how this one has the V. We're talking about vaporization because there's different values for those that are given. So I would have to give you what those values are. So on the next page, we're going to look at some examples. So we have 2 beakers, A and B. They both contain 100 grams of 2 different substances. If you notice, the change in vaporization for water is 2,260 grams, and for ammonia, it is 1,369. If they're both heated, which one will become dry first? So it's becoming dry. So that means we are changing from a liquid to a gas. Okay? Well, guess what? If this one has this value and this one has this value, isn't this one easier to change in state? So it would be the ammonia. Which one has stronger attractions? Well, the one with the stronger attractions is the one that's going to be more difficult to change in state. So now we're going to look at 2 examples of calculating this. The question is, they gave you what the heat of fusion was for water, and they gave it both in moles and in grams, and then they gave you the heat of vaporization. So we want to write the chemical equation for this, and we want to do the LOL diagram, and then we want to calculate. So if I look at this first one, it looks like I have ice. So I've got a solid, and this is what I'm looking at for my substance. And it looks like it is at 20 degrees. No, it's at 0, so it's frozen at the beginning. And I want to figure out how much does it take to melt that. All I'm going to do is melt it, so I'm just going to change the phase. And we know when it goes to that melting, it's staying the same. So that means, looking at my units, looks like this has to absorb Q, right? So it's endothermic. So this means if I was to write my equation, aren't I starting out as ice, as a solid? It's going to absorb, right here I'm saying that, heat, and it's going to become water. That is a liquid now. Here's my equation. You can take it right off of the LOL diagram. Now, if I'm changing in state, the only equations I need are Q, and it could be upper or lowercase, equals the mass times the change in H for either fusion, or it could be change in H for vaporization. In this example, it looks like we're going to use heat of fusion because we're changing from a solid to a liquid. So all we would do would say equals, I have 20 grams, and since I have grams given to me here, I want to use the constant that has grams in it too, so that I get units to cancel out. And that should give me my answer, and I got like 6,680 joules. It looks like I have, one sig big, so it'd be about 7,000 joules. That's how much it's going to absorb. So we're going to do one that is the reverse of that. They want the equation for the condensation of water vapor. How much heat is released? There's our heat. There's our clue right there. That we're going to be releasing heat from this. So we're going to start out with this vapor. And it's a vapor, so it's going to start out with 4 bars. And it's at 100 degrees, so it's very hot. 4 bars. And the temperature is staying the same. We know that we don't have a change in temp when it changes state, but the state changes. It becomes a liquid. In this case, it looks like 2 bars need to exit. There's my Q, so it's exothermic. If I wrote my equation here, I'm going to start with this vapor, water vapor. I'm just going to write it as water and say it's a gas. I'm going to release heat right here, showing that. Plus then I'm going to be left with water that is a liquid. There's my equation. Now for this one, Q equals the mass, and since we're talking about between a gas and a liquid, it's going to be the heat of vaporization. Now, this time for your mass, you have 1.11 moles. So since I'm given moles, I'm going to need to go up and look at the constant, and I need to use the one that is for moles. But I'm talking about heat of vaporization, so I'd have to use this one right here. Okay, because we're going from a gas to a liquid. So that number is 40.68 kilojoules per mole. Now, the other thing that I got to recognize is this is being released. If it's released, this should be a negative value. Right? It's exothermic here. I'm going to make this a negative value here, a negative 40. When I do my math, I got a negative 45.2 joules. That's how much was released. So that would be the answer to this. Now, you should be able to go and we're going to do a problem with a heating curve.